Hello, this is Mrs. Poland again. This is Lesson 6.11, Example 2. According to the National Institute for Occupational Safety and Health, job stress poses a major threat to health of workers. A news report claims that 75% of restaurant employees feel that their work stress has a negative impact on their lives. Managers of a large restaurant chain wonder whether this claim is valid for their own employees. A random sample of 100 employees finds that 68 answer yes when asked, does work stress have a negative impact on your personal life? Is this good reason to think that the proportion of all employees in this chain who would say yes differs from 0.75? Support your answer with a significance test. So again, we're going to go through this 4-step process. So we're going to state the parameter, hypotheses, and significance level. Okay. So P is the true proportion of all employees in this chain who would respond yes. So the null hypothesis is going to be, notice it, I forgot to mention that in this step when we define a parameter, there's no hats. Be careful. So our null hypothesis is rho is equal to 0.75. In the null hypothesis, it's only parameters, and for the null, it would be equal to some sort of number. And the alternative, P is, and it's either going to be less than, greater than, or not equal. In this case, there's no indication within the problem scenario of which direction, so then you would use not equal. And did they give you a significance level to use? No, they didn't. So you can choose anything, but most of the time we choose 0.75. So we're on to the next step. And so step 2. So step 2, we're going to verify the conditions. And again, these are pretty much the same conditions with some minor adjustments as we had done in the 1 proportion z interval. So the first condition is random sample as stated. And again, the reason for this is so we can generalize our results to the population of interest. The second condition, it's reasonable to assume that there are more than 1,000 employees in this large restaurant chain. So that's the 10% condition. And the reason for it is it allows us to sample without replacement. And the last condition is that large count condition. Be aware that in this case, we're using the parameter. And again, the reason why we're using the parameter as opposed to P hat is P is defined in the null hypothesis. That 0.75 is assumed to be true. So that's what you have to use in the large count condition and in the standard error. The reason for the third condition is it allows us to approximate the sampling distribution with a normal model. That should say normal. Distribution. Okay. So now we're up to step 3, which is the large count, which is the calculations of the test statistic and the p-value. So the test statistic is defined as z for proportions, and it's p hat, the statistic, minus the parameter over the standard error. The standard error is PQ over N, Again, we're using P and not P hat because P is defined in the null hypothesis. So specifically, what are we filling in? Well, we know that let's go back up. We know that P hat is 68 out of 100, or 0.68. And so now we're going to substitute that in. So 0.68 minus 0.75 is our parameter. And again, in our test statistic, we're using the 0.75 times Q is 0.25 over 100. Notice that N is also under that radical. And so we're going to put this into, and we get negative 1.6166. And so let's continue. We have to calculate the p-value, but it's really helpful to draw a diagram. So we draw a bell curve. Our mean of the sampling distribution is p, which is 0.75. And we ended up getting a test result of 0.68. And remember, we're looking at the not equal case. So in the not equal case, you have to look at below, but then the equivalent if it's above, because when it's not equal, we really don't know, or the person who created the study wasn't quite sure which way the direction of the difference would go. So the Z statistic was negative 1.61. I think I need to recalibrate the pen later so it writes more neatly. Hopefully you can bear with it for the time being. And so the p-value is going to be the probability, or actually twice the probability that our p hat in this case is less than negative 1.6166. That's twice the probability that Z is going to be less than negative 1.6166. So the key point I want you to see here is that when you have that not equal case, what you're doing is you're doubling the area to whichever extreme you're going for. So if I have a negative Z statistic, you're doubling that area under the curve. So this is going to be twice normal CDF. And when you enter this in the calculator, you should get an answer of 0.106 approximately. Okay, let me make that 106 better. And that's your p-value. Sorry about this. This is 0.106, but it's not typing well. Again, I have to recalibrate the pen later today. So it's a pretty large p-value. So we're up to the final step about stating the conclusion. So this is actually step 4. This one was meant to be step 3. So for the first part of step 4, we interpret the p-value, assuming HO is true. In other words, rho is 0.75. There is 0.106, that's your p-value. Probability of getting a sample proportion of 0.68 or more extreme, or a more extreme value purely by a chance. So with a not equals case, since we really don't know if it's less than or greater than until we get the sample proportion, we normally just say more extreme as opposed to greater than or less than. You're then going to make your conclusion, and since our p-value is greater than 0.05, in this case we're failing to reject HO, We do not have convincing evidence that the proportion of employees that respond yes differs from the 0.75.